today's seminar. Today's seminar is a special seminar due to the coronavirus. This is online. And thank you for taking time to attend this seminar. My name is Chunfu Xin. I'm a Ph.D. student in the Department of Civil and Environmental Engineering at USF. And I just make my dissertation defense, I think 3 weeks ago. And today's presentation is part of my dissertation work. Let's move to the topic. I will share my desktop. Can you see the PPT?
Yes, we can see it.
Okay, thank you. Today I want to talk about post-overlay flexible pavement performance modeling. And in the presentation, I will talk from these following 6 aspects. First, I will talk about the research background, and then problem statement, literature review, research objectives, and the core part, post-overlay pavement performance modeling. And first, before I talk about the modeling part, I want to give you some general concept of the background. What's the flexible pavement? And what's the flexible pavement distress and the roughness? And what's the pavement management system and performance modeling? First, what's the flexible pavement? The flexible pavement is the pavement that is surfaced with the asphalt material. Since it is a multi-layer structure, as we can see in figure 1, this is a multi-layer structure. The first layer is surface course, and then base course, sub-base course, and subgrade. And since the overall structure is flexible, it's soft, when the traffic load is on the surface and the pavement will deflect. So we also call the asphalt pavement as flexible pavement. When the pavement is constructed, the pavement condition will deteriorate and some pavement distresses will appear, as we can see in the figure 2. Some as vertical cracking, some are rotting, and I think this is common in our daily life. When the pavement distresses progress, the smoothness of the pavement surface will decrease. The IAI International Roughness Index is a performance indicator to evaluate the smoothness of the pavement. The definition of the IAI is calculated as the accumulative suspension, vertical suspension to the distance that the vehicle traveled at a speed of 50 miles per hour. And when the pavement has a lot of distresses, the smoothness will decrease, and the vehicle operating cost and its corresponding environmental impact will increase. As we can see in figure 4, this is a general IR curve on one pavement section. First, it will increase with time, and then when the pavement maintenance and rehabilitation activities are implemented, the roughness would be reduced, and then it increases again. Asphalt overlay is the typical pavement maintenance and rehabilitation activity. Asphalt overlay is the new layer that paved on the existing pavement. Sometimes when the pavement suffers severe distresses, the milling technique will implemented. It means some part of the existing pavement will be removed, and then a new layer will be paved. In order to schedule the pavement maintenance and rehabilitation, especially for asphalt overlay activities, the pavement management system is needed. Since pavement management system is a tool that helps heavy agency to make decision to rehabilitate the pavement or select which pavements that are needed to be rehabilitated. The pavement management system includes 3 parts. The first, as we can see in figure 7, The first part is data collection, like the pavement condition test machine, the vehicle will drive down the road and collect the surface data. And then based on the data and the pavement structure information, environmental information, traffic information, the performance model can be developed to predict the future performance. And then based on the predict the future performance and some quantitative analysis like life cycle analysis, the maintenance policy or rehabilitation policy can be selected. As we can see in figure 8, this is the general post-OLE pavement performance model that I developed in the study. First, it will decrease, as we can see in the previous one. It decreased since the pavement was rehabilitated, and then the roughness will increase. And then when the pavement deteriorates to a certain level, the asphalt overlay will be implemented again and then reduce and then increase. This is general post-overlay pavement performance model. And in this study, I will talk about how to develop this curve. And before that, I also want to touch a little bit about life cycle analysis, since this is the method to quantify the economic cost or environmental impact of different asphalt overlay policies on over a certain time period. For example, figure 9, this is a life cycle cost analysis. Life cycle cost analysis is try to evaluate the economic cost of a pavement system over a certain time period. Life cycle assessment showing in figure 10 is used to evaluate the effects of the pavement on environment. So this is the general background about this research. I hope you can grasp a big picture. And then I want to talk about the problem statement. In the problem statement part, I will talk about the general background and the current situation of the pavement. In the US, more than 19% of the US paved roads were constructed before 2000, even before 1990. After so long time service, the pavement condition will deteriorate. The ASCE has awarded the poor condition, like overall grade of the D- or D or D+ to US road from 1998 to 2017. Also for FHWA, also estimated that if we want to rehabilitate the pavement or to keep the road condition in a good service, $170 billion is needed every year. Since so large portion of this investment will be used for asphalt overlay policy. Given this large amount of the annual investment and the large inputs of the energy and natural resources in the asphalt overlay projects, significant budget saving and environmental benefits can be achieved by selecting the optimal asphalt overlay policy. But how to select the optimal asphalt overlay policy? First, we need to predict the pavement post-overlay pavement performance in a good accuracy, right? So the post-overlay pavement performance model is the key part to bridge the overlay policy with the future life cycle cost analysis and environmental impact. So in order to understand the situation about the post-overlay pavement performance modeling, a comprehensive literature review was conducted. First, what's the data that previous studies used for pavement performance modeling? And what are the methods that they used? And what's the potential issues existing in the current studies? And what are the research gaps? These are some questions we need to answer by conducting literature review. As we can see in slide 15, payment performance data used in the previous studies can be classified into two groups, like testing data and the payment condition survey data. The testing data has the major drawbacks. The drawbacks is that the test data cannot reflect the long-term climate effects and actual missed traffic. So normally we use payment condition survey data in payment management system. The payment condition survey data can be classified in two levels, the national level and the local level, local state level. The LTPP database is the national level data that launched by FHWA. Since the LTPP data can cover the overall national climate regions, it is much better than local level data. For the measures, for the model measures that's used for the general payment performance model, first I want to talk about the difference between general payment performance model and the post-overlay payment performance model. The difference between these two is the previous one does not consider the maintenance, the effects of maintenance and rehabilitation activities on payment performance deterioration. The post-overlay payment performance model are focused on to evaluate the S4 overlay design on future payment deterioration process. The general payment performance model can be classified into these two groups, mechanistic empirical model and empirical model. Based on the statistical methods that they used in empirical model, they can be classified into four groups, like artificial neural networks, regression models, survival models, and Markov models. Our focus is post-overlay payment performance model. So the previous studies were reviewed in much details. Based on the literature review on post-overlay payment roughness model, we found that no post-overlay roughness progression model was established by fully considering the combination effects of the overlay design, original payment performance, payment structure characteristics, traffic loadings, and climate factors. In addition, most of the previous studies only consider two S4 overlay thickness level, like a thin overlay and a thick overlay, like a 2-inch, 5 inches. They didn't consider the continuous variable of the overlay thickness on the payment deterioration. In addition, some statistical modeling issues existed in the previous models, such as endogenous overlay design, section-specific unobserved heterogeneity, and within section severe correlation issue. I will talk about these issues in the next slides. Also, for the survival analysis that try to evaluate the distress, the payment distress, we found that the also like no post-overlay distress initiation model was established by fully considering the combination effects of the previous one, like overlay design, original payment performance, payment structure, and traffic loading, climate factors. In addition, like the endogenous overlay design issue, section specific unobserved heterogeneity issue, and the data censoring issue are not addressed. So for the statistical modeling part, several issues may exist, such as selection bias. If we, for example, if we model the payment crack initiation or progression, we only select the crack data, we may suffer selection bias, since at the end of the payment condition survey, some payment may have crack. Some payment section may not. If we only select those payments have cracked, we will suffer selection bias. The second issue is the multicollinearity. The multicollinearity is will occur when two or more independent variables are highly correlated with each other. For example, payment age and accumulative traffic volume are highly correlated. Since accumulated traffic volume is calculated by annual traffic times payment age. So if we put these two variables in one model, the efficiency of the modeling would be effect. Also, for the third issue is unobserved heterogeneity. Unobserved heterogeneity issue will occur when some unobserved factors are correlated with observed variables that are developed in the model. They may lead to an unobserved heterogeneity issue. May cause the parameter estimation bias issue. The fourth issue is the severe correlation. The severe correlation is occurred because of the payment deterioration is a time series process. When the severe correlation occurs, the error will propagate with the time. Also, for the endogeneity issue, since S4 overlay is designed by heavy engineer, the heavy engineer will design the overlay policy based on the previous payment condition and the traffic. If the previous payment condition is bad and the traffic is heavy, maybe the overlay thickness will be thicker. So the overlay thickness variable or overlay design is an endogenous variable. So we need to address that. The sixth issue is the censoring issue. Censoring issue is that payment session have not yet failed by survey time, such as cracking. We will find a lot of the payment sections are not cracked when we develop the survival analysis. If we only consider the cracked payment section, the censoring bias issue will occur. So based on the research gap identified in the literature review and the potential issues that are summarized in the slides, and the research objectives can be clearly illustrated. In the presentation, the two objectives are: one, to develop a comprehensive post-overlay distress initiation model with the national level data, LTPP data. Two, to develop a comprehensive post-overlay flexible payment roughness progression model with the national level data. If we can predict when the payment crack occurred, then we can implement crack sealing like payment maintenance activity. If we know how the payment deteriorates in the future, we can set a failure criteria, and then we can schedule S4 overlay timeline. So in order to develop the post-overlay payment distress forecast model, the first I need to collect the data. And then based on the data collected, we need to get the descriptive analysis of the data. And then based on some statistical measures, payment distresses forecast model can be developed. Based on the model estimation results, the discussion of the results can be implemented. So first, data collection. the data was collected from two databases, the FHWA LTPP database and the NOAA climate database. The selected payment sections are illustrated in Figure 12. These payment sections are from three LTPP programs. The potential variables for the model development are collected from LTPP different models and the NOAA database, such as the design of the overlay and the existing payment structure and the existing payment performance and the traffic loadings and the climate factors. This is a descriptive of the overlay design. As we can see, as for overlay thickness, are varied from 0.5 inch to 9 inch, and about half of the as for overlay projects are milled before paved. And this is table 2, a descriptive analysis of potential variables. As we can see in slide 13.1, as we can see in figure 13, this is the survival probability of the vertical cracking. As we can see in this figure, we know that after 5 years, about 80% of the pavement section will not have crack. And also, we can do this for severe rotting, wear past longitudinal cracking, non-wear past longitudinal cracking, and transverse cracking, different types of the cracking. And since this Kaplan-Meier product limit estimation survival probability is based on the actual data, that this is a non-parametric survival analysis. If the figure 18 illustrates the different types of the payment distress initiation time, as we can see, non-wheel pass longitudinal cracking will first appear, and then transverse crack, and then vertical cracking, and wheel pass longitudinal cracking and severe rotting. But for specific payment section, the payment distresses, different types of the payment distresses may occur in different orders. The methods that are used to evaluate the distress initiation model is the random parameter Weibull duration model. This method is used to evaluate the time to distress initiation. We can say this can be as we can see here, it can be addressed the sensor data and unobserved heterogeneity issue. And then the model can be developed. As we can see here, this is a random parameter that the deflection, the payment deflection has the random effects on the vertical crack initiation. The specific effects of the contributing factors to different types of the distress initiation are illustrated here. As we can see, this is the hazard ratio. If the hazard ratio is less than 1, it means it will decrease the rate of the distress initiation. For example, with 1 inch increase of the asphalt overlay thickness, about 27% of the vertical crack initiation probability will be reduced. Similarly, if we use recycled material the fatigue cracking initiation probability will increased by 80%. Summary. As we can see here, the endogenous overlay design issue has significant effects on all pavement distress initiation. The endogenous overlay design was addressed by considering the LTPP GPS data as endogenous design. SPS data is experimental design. So for SPS pavement study, there are control. This is a control group. Also, we can say pre-overlay pavement distress have significant effects on post-overlay pavement distress initiation. Also, like traffic volume, with the increase of the traffic volume, the fatigue cracking initiation and the rutting, severe rutting occurrence probability will increase. Also, for the climate effect, the longitudinal wheel pass and non-wheel pass and the transverse cracking will be significantly affected by the climate. This is general findings, the major findings from the model discussion. The second part, I want to talk about how to develop the post-overlay pavement roughness progression. The data that's used for roughness progression is similar to the previous data. First, the descriptive analysis. The initial II is the original pavement II roughness. The II reduction is the reduction value between original pavement II and as-built II after the asphalt overlay activities implemented immediately. And as we can see here, the II reduction value is increased linearly with the original pavement II. However, the as-built II, the relationship between as-built II and original pavement II is not very clear. So in the model development part, instead of using as-built II as dependent variable, the II reduction value was used as the dependent variable. As we can see in figure 20, this figure is trying to evaluate the II progression trend with the time. As we can see here, the relationship between II progression and the pavement age is nonlinear. Also, we see the error bar is increased with the time. It means the positive severe correlation may exist. And the research method to evaluate these two relationships, two curves, is I used the random coefficient linear regression with autocorrelation. First of all, the II reduction is the general multiple linear regression. And also, unobserved heterogeneity issue was addressed. For the post-overlay roughness progression, first, this trend was evaluated as the exponential equation. So this form was used. And then the section-based specific heterogeneity issue and unobserved heterogeneity issue, and within section severe correlation issue are addressed with different equations. And this is the II reduction model estimation results. As we can see here, the endogenous overlay design issue has a random effects on the II reduction. The overlay thickness has a positive effects on the II reduction. It means with the increase of the S4 overlay, the II reduction value will increase. Also, we see the fatigue cracking and the rotting. If the previous pavement has a lot of the fatigue cracking, the II reduction value will increase, since a lot of the cracked will be addressed by overlay. However, if the previous pavement suffers severe pavement rotting issue, the II reduction value will be reduced. Because when the previous pavement has severe pavement rotting, it means the existing pavement evenness is a problem. And when we implement a new layer on the existing pavement, the unevenness is also exist. This is the validation part of the II reduction model. The horizontal axis is the observed II reduction. The vertical axis is about the predict II value. As we can see, the II reduction model forecasts the future, like the II reduction, pretty well. The second part is to evaluate the post-overlay II progression rate, like this part, the slope of this curve. As we can see, as for overlay thickness, will decrease the II progression rate. Also, the interaction term between overlay indicator and the relative fatigue cracking area has significant effects on II progression rate. This means if the previous pavement has fatigue cracking, but not milled, it will increase the II progression rate. If the previous pavement was milled, even the pavement suffers severe fatigue cracking, the post-overlay II progression rate will not increase. Also, the pavement structure and the material characteristics, like FWD deflection. FWD deflection is a test data that used by FWD machine. They will implement a load on pavement and then measure the deflection of the pavement surface. If the pavement surface deflection is large, it means the pavement structure capacity is small. So as we can see, if the pavement structure capacity is reduced, it means the II progression rate or pavement deterioration rate will increase. Also, the traffic and freezing climate factors are found to have significant effects. For the model validation, as we can see in figure 22, if the correlation, autocorrelation, is not addressed, it will suffer severe bias issue. Table 6 summarizes the effects of the contributing factors on post-overlay II progression. First as built II, then future II progression rate. As we can see here, overlay thickness will reduce as built roughness. also reduce the future roughness progression rate, meaning will reduce the as-built roughness, also reduce roughness progression rate if severe fatigue cracking occurred. Recycled material does not affect either as-built roughness and future roughness progression. It means we can use recycled material to achieve significant environmental benefits. Also, endogenous overlay design has random effects on as-built roughness. Pre-overlay or existing pavement distresses also have significant effects on as-built roughness. Also, pavement structure deflection, subgrade tap, traffic volume, and climate factors. They are all found to increase the IA progression rate. The endogenous overlay design issue was illustrated in figure 27. As we can see in figure 27, the left figure, if the pavement is endogenous, like GPS data, it means the pavement overlay policy was determined by heavy engineer, not determined by randomly select. So it can be seen the slope is larger. It means more pavement distresses will be addressed, or thicker asphalt overlay will be implemented when original pavement suffers severe pavement distresses. The effects of the endogenous overlay design on as-built II is random. It means about 80% of the asphalt overlay projects, the endogenous overlay design will increase the II reduction value, or will lead the smoothness of the as-built II. Summary. This is the summary based on the post-overlay roughness progression model. As we can see here, relative to random coefficient post-overlay roughness progression model, if we incorporate the within section severe correlation, the mean absolute percentage error of prediction value would be reduced. In addition, relative to exogenous overlay with the same design, endogenous overlay can reduce as-built pavement roughness by an average of 5.4% of the original pavement roughness. The fourth part is the third conclusion. The third finding is that as-built pavement roughness would decrease by 1.35 inches per mile with a 1 inch increase of asphalt overlay thickness. Also, relative to asphalt overlay with the same design, milling before overlay can provide a smoother as-built roughness pavement by reducing 7% more of the original pavement roughness. The fourth part is relative to a virgin asphalt mixture. The application of 30% of the recycled material would not affect as-built pavement roughness or future roughness progression rate. This is my presentation. Thanks to the funding support from CTEC, FDOT, CSA, and USDOT. Thank you for your attention. Any questions? Hello? Hello, everyone.
Yes, we can hear you.
Hi. I don't know how did you feel about the presentation? Since
Presentation was good.
Thank you. And do you have any questions?
I don't have much questions.
Okay, thank you.
Oh, thank you, Chunfu. I have one question.
Okay.
So I see in your models, you got some variables with random parameters, right?
Yeah.
So what the reasons? I mean, what missing variables you think that can account for those random effects?
Okay. Thank you for raising this question. Since we cannot collect every data from the field, some construction record of the asphalt overlay projects may not be collected by heavy engineer. So when we develop the models, if the unobserved part, such as the construction record, material, they may be section specific difference from one section to another. So if that part are correlated with observed section specific factor, the endogenous, the heterogeneity issue will occur.
So
Like
I mean,
sorry.
Yeah, I mean, I know that it's very difficult for you to collect some very specific variables like material or specifications of construction progress. But I mean, what is the most potential variables that can that you think? Yeah, I mean that you think can explain the unobserved effects for the II change.
I think, for example, as we can see, the endogenous overlay design is a random, as we can see in the presentation here. Endogenous overlay indicator, like in page 46, endogenous overlay is a random effects. It means the pavement section was designed in different by different people. The endogenous bias for different pavement section may vary from one section to another. So that's why the effect of the endogenous overlay on the roughness reduction is random instead of fixed effects.
Thank you.
Yeah. Any other questions?
Does anyone else has another question? Guys, I think Dr. Lee is not here in the presentation, but thank you, Chunfu Xin, for the presentation. Great job, yep. And yeah, I hope you all have a great Friday. And that's it. Thank you for the participation for everyone.
Thank you. Thank you all for your time.
Thank you, everyone. Stay safe. Take care.
Stay safe. Thank you.
Thank you.
Yeah.